The history of AI is the history of humanity's effort to recreate intelligence through computers. It began in the 1950s with the era of logic and symbolic processing. During this period, researchers represented human knowledge as symbols and logical rules, allowing computers to perform reasoning through formal inference. In the 1960s and 1970s, AI entered the era of rule-based systems. Search algorithms, inference engines, and expert systems captured the knowledge of specialists as explicit rules, enabling computers to support decision-making in specific domains. During the 1980s and 1990s, machine learning introduced a major shift. Instead of relying on manually written rules, computers began learning patterns directly from data, dramatically improving prediction and classification. From the 2000s onward, deep learning transformed AI once again. Large-scale neural networks automatically learned complex features from massive datasets, leading to remarkable advances in image recognition, speech recognition, and many other applications. The next milestone was the rise of large language models, or LLMs. Rather than recognizing patterns alone, these models learn relationships, context, and meaning from enormous collections of text, enabling natural conversations, reasoning, and content generation. Today, AI is entering the era of multi-agent systems, where multiple AI agents collaborate, communicate, and coordinate with one another to solve increasingly complex and dynamic problems. Looking back, we can see that AI has continuously evolved, from logic, to rules, to data-driven learning, and now to collaboration among intelligent agents. However, this remarkable progress has also introduced entirely new challenges. As AI becomes more capable, issues such as reliability, safety, fairness, transparency, interpretability, collaboration, and accountability become increasingly important. In the following slides, we will explore these emerging challenges and discuss why addressing them is essential for the next generation of AI systems. The emergence of generative AI may make it seem as if artificial intelligence appeared overnight, but in reality, today's AI is the result of more than 70 years of continuous research and technological progress. The journey began in the 1950s, when the invention of computers inspired a fundamental question: can machines think? In 1950, Alan Turing proposed what became known as the Turing test. Then, in 1956, the term artificial intelligence was officially introduced, marking the birth of AI as a scientific field. Over the following decades, researchers focused on how to represent human knowledge and enable computers to reason with it. This led to the development of expert systems, knowledge engineering, and ontologies, laying the foundation for intelligent systems that could make decisions using structured knowledge. Around 2010, another major transformation took place. The combination of massive datasets, powerful GPUs, and advances in machine learning enabled deep learning to achieve remarkable breakthroughs. AI began to surpass human-level performance in tasks such as image recognition and speech recognition, making it a practical technology for many real-world applications. The next milestone arrived in the 2020s with the emergence of large language models, or LLMs. These models gave AI the ability to understand, generate, and communicate through natural language, bringing generative AI into everyday life and transforming the way we work, create, and use knowledge. Looking back, we can see that AI was not created overnight. It is the result of decades of progress, from logic, to knowledge, to data, and finally to learning. Today's generative AI stands on the foundation built by generations of researchers, each contributing another step toward intelligent machines. The first generation of AI was AI that solved problems through logic. To understand why, we first need to look at the evolution of computers themselves. Everything began with the invention of the transistor. A transistor is an electronic switch that uses a small electrical signal to control a much larger current. It became the fundamental building block of every modern computer. The next breakthrough was semiconductor technology. By integrating millions, and eventually billions, of transistors onto a single silicon chip, engineers were able to build increasingly powerful and reliable computers. These transistors were then connected to form logic circuits. Basic logic gates such as AND, OR, and NOT could be combined to create arithmetic units, memory, and control circuits, the essential components of every computer system. The same idea of logic was later applied to human reasoning. This gave birth to the first generation of AI, known as symbolic AI. In symbolic AI, knowledge is represented as symbols, facts, and rules. The AI does not learn from data. Instead, it applies logical inference to the knowledge it has been given. The process is straightforward. Facts and rules are provided. Logical reasoning is performed, and a conclusion or answer is derived. In other words, the intelligence comes from explicit knowledge and logical reasoning, rather than learning from experience. This is the foundation of the first era of AI. The origin of artificial intelligence was not machine learning. It was the representation of knowledge through symbols and the ability to reason logically from that knowledge. Before we continue exploring the history of AI, let's first understand how a computer itself works. Everything begins with the transistor. A transistor is a tiny electronic switch that controls whether electricity flows or not. By switching electrical signals on and off, it represents the digital values of 0 and 1, the fundamental language of every computer. When transistors are combined, they form logic gates such as AND, OR, and NOT. Each logic gate performs a simple logical operation, taking one or more inputs and producing an output according to predefined rules. Although each operation is simple, combining millions, or even billions, of these logic gates creates something much more powerful. They become the CPU, or central processing unit, which serves as the brain of the computer. The CPU performs calculations, controls hardware, and executes every program we use, from web browsers to scientific simulations. In other words, a computer is not a mysterious machine. It is an enormous computational system that continuously processes digital signals by performing logical operations at incredible speed. The applications we use every day, and even modern AI systems, ultimately run on this same foundation of logic circuits. Understanding this simple progression, from transistors, to logic gates, to the CPU, and finally to the computer, is the first step toward understanding how artificial intelligence became possible. When computers were first invented, the concept of programming did not yet exist. In the beginning, functionality was created by designing the hardware itself. Engineers built computers by connecting logic circuits, with each circuit performing a specific task. As computers became more powerful, however, people wanted to use the same hardware for many different purposes. This led to one of the most important innovations in computing: programming. At the lowest level, a computer understands only machine code, a sequence of zeros and ones. Although machine code is efficient for computers, it is extremely difficult for humans to read and write. To make programming easier, assembly language was introduced. Assembly language replaced binary numbers with symbolic instructions, making programs much more understandable for programmers. The next major step was the development of high-level programming languages such as Fortran, Lisp, and COBOL. These languages allowed developers to describe algorithms and processes without worrying about the underlying hardware. In other words, software development evolved from writing circuits, to writing instructions, and finally to writing complete programs. This transformation turned computers from specialized calculating machines into general-purpose systems capable of solving an enormous variety of problems. More importantly, the ability to describe knowledge and rules in software laid the foundation for the first generation of AI, symbolic AI. The evolution of computers was therefore not only an evolution of hardware, it was also the transition from directly controlling physical circuits to describing knowledge, algorithms, and intelligence through software. As computers became more widespread, programming evolved beyond simply writing instructions. People began describing the procedures for solving problems themselves. These procedures are called algorithms. An algorithm is a step-by-step method for solving a particular problem. Whether we are sorting data, searching for information, performing numerical calculations, or running simulations, the computer follows an algorithm to complete the task. Every computation follows the same basic flow. First, the computer receives input. Next, it executes the algorithm, a sequence of logical steps that processes the data. Finally, it produces the output, the result of the computation. In this sense, a computer is simply a machine that faithfully executes algorithms. To make writing algorithms easier, programming languages continued to evolve. Fortran became one of the first high-level languages for scientific computing. C provided a powerful language for operating systems and high-performance software. More recently, Python has become one of the world's most widely used programming languages because of its simplicity, readability, and strong support for AI and data science. The important point is that programming languages are not the goal. They are simply tools for expressing algorithms in a form that humans can understand and computers can execute. This idea, that humans design algorithms and computers execute them, became the foundation of computer science for many decades. The earliest AI systems were built on exactly this principle. Researchers believed that intelligence itself could be achieved by describing knowledge and reasoning as algorithms that computers could execute. As computers became more powerful, numerical computation and scientific simulation grew increasingly important. This also changed the way software was written. In the beginning, programmers described problems as a series of individual rules and step-by-step procedures. But as problems became more complex, this approach became difficult to manage. A higher level of abstraction was needed. This led to the concept of the function. Instead of describing every individual step, programmers could express computation as a mathematical relationship between inputs and outputs. In other words, software evolved from rules, to formulas, and finally to functions. A function is a simple but powerful idea. It receives an input, applies a defined relationship, and produces an output. Mathematically, we often write this as y equals f of x. Once the input is given, the function determines the corresponding output. This way of thinking became one of the fundamental principles of modern software engineering. Programs were no longer viewed simply as collections of algorithms. Instead, they became systems built by combining reusable functions. This shift was more than just a programming technique. It represented a new way of describing computation itself. As we will see in the next stage of AI, the concept of a function became even more important. Rather than manually writing every rule, machine learning would begin to learn the function itself directly from data. This marked the beginning of a completely new era in artificial intelligence. So far, we have seen that early computers were machines designed to execute predefined procedures. They followed logic circuits, machine code, and programs to carry out instructions accurately. In other words, they operated in the world of procedures. But as computer science advanced, a major turning point emerged. That turning point was the abstraction known as the function. A function is a relationship that receives an input and produces an output. Mathematically, we express it as y equals f of x. This simple idea allowed complex computations to be represented as a single reusable concept instead of a long sequence of individual steps. Functions could be combined, reused, and composed to build increasingly sophisticated systems. More importantly, functions became a common language shared by both computer science and mathematics. Once computation was expressed through functions, computers could directly handle mathematical concepts. Calculus, including differentiation and integration, linear algebra, with vectors and matrices, probability and statistics. All of these mathematical frameworks could now be implemented naturally in software, and this mathematical foundation eventually led to optimization, machine learning, and artificial intelligence. In modern machine learning, a model itself is represented as a function. Rather than writing rules by hand, we train the parameters of that function using data. In other words, the goal is no longer to program every decision explicitly. Instead, we learn the function that best maps inputs to outputs. This was a fundamental shift in the history of computing. By adopting the abstraction of functions, computers evolved from machines that simply execute calculations into machines capable of expressing and manipulating mathematics itself. And this transformation became one of the most important foundations of modern AI and deep learning. This brings us to the second era of AI. Computers evolved from machines that simply perform calculations into machines that can learn. At the heart of this transformation is machine learning. Machine learning is a technology that discovers patterns and relationships from large amounts of data, then uses what it has learned to make predictions and decisions about new, unseen data. Unlike earlier AI systems, humans no longer write every rule by hand. Instead, we provide data, and the computer learns the most appropriate function, or model, directly from that data. The model is then evaluated, refined, and improved through repeated iterations, gradually achieving higher accuracy. But why did machine learning become possible? The answer lies in the abstraction of functions. Once computers could represent computation as mathematical functions, they could directly apply powerful mathematical tools. Optimization through differentiation and gradient descent, linear algebra using vectors and matrices, probability and statistics for modeling uncertainty, and function approximation for representing complex relationships. These mathematical foundations made it possible for computers to learn models from data instead of relying on manually designed rules. As a result, machine learning opened the door to a wide range of applications: image recognition, speech recognition, demand forecasting, natural language processing, reinforcement learning, and ultimately, generative AI. Machine learning is therefore much more than a collection of algorithms. It is a framework in which computers improve through experience by continuously learning better mathematical models from data. This marked a major turning point in the history of AI. Computers had evolved once again, from machines that calculate into machines that learn. This brings us to the third era of AI, the era of deep learning. Machine learning enabled computers to learn from data, but solving more complex problems required an even more powerful learning mechanism. The key breakthrough was differentiation. In mathematics, differentiation measures how a function changes. For machine learning, it tells us which direction we should adjust the model's parameters to reduce error. Using this information, the model can repeatedly update itself, becoming a little more accurate after every iteration. This process is the foundation of deep learning. By stacking many layers of neural networks together, deep learning can gradually learn increasingly complex and abstract features. Instead of relying on manually designed features, the network automatically discovers useful representations directly from data. As a result, deep learning achieved remarkable breakthroughs in image recognition, speech recognition, natural language processing, prediction, and many other fields that had previously been difficult to solve. However, deep learning comes with an important challenge. Training these large neural networks requires an enormous amount of computation. During training, the system repeatedly performs massive matrix operations while calculating gradients through backpropagation. This is where GPUs became essential. Originally designed for computer graphics, GPUs are capable of executing thousands of mathematical operations in parallel. That makes them ideally suited for the large-scale matrix computations required by deep learning. With the introduction of GPUs, training that once took weeks could be completed in days, or even hours. Larger datasets and deeper neural networks became practical, accelerating AI research and real-world applications. Deep learning is therefore the result of three technologies working together: deep neural networks, optimization through differentiation, and the massive computational power of GPUs. Together, these advances transformed deep learning into a practical technology and laid the foundation for the next major breakthrough: large language models, or LLMs. This brings us to the fourth era of AI, the era of large language models, or LLMs. Previous generations of machine learning focused primarily on learning patterns from large collections of historical data. Their main goal was to classify, predict, or detect patterns that already existed. In other words, they learned static patterns from the past. LLMs represent a fundamental shift. Rather than simply extracting fixed patterns, they process the continuous flow of language and dynamically construct meaning based on context. The meaning of a word is not fixed. It depends on the surrounding sentence, the conversation, and even the user's intent. LLMs continuously interpret this evolving context to generate the most appropriate response in real time. In other words, AI has evolved from recognizing static patterns to understanding dynamic patterns. This capability has enabled a wide range of new applications: natural language generation, question answering, summarization, translation, code generation, and even creative idea generation. As a result, the role of AI has changed dramatically. Traditional AI focused on predicting the correct answer from existing data. LLMs go a step further. They understand context, integrate knowledge, and generate new expressions and solutions that fit the current situation. You could say that AI has moved from the world of static data to the world of dynamic context. It has evolved from processing individual words to understanding meaning, engaging in dialogue, and combining knowledge to create new value. Large language models are therefore much more than systems that memorize information. They dynamically reconstruct meaning within the flow of language, enabling AI not only to understand the present but also to generate new knowledge, ideas, and future possibilities. As we have seen, large language models, or LLMs, have evolved into AI systems capable of understanding natural language and generating text, images, code, and much more. But the evolution of AI does not stop there. Today, a new frontier is rapidly emerging: multi-agent systems. Generative AI has greatly enhanced the capabilities of a single AI assistant. Given a user's instruction, one model can analyze information, answer questions, generate content, and assist with a wide variety of tasks. In other words, it represents the power of individual intelligence. Multi-agent systems take the next step. Instead of relying on one AI, multiple specialized AI agents work together toward a shared goal. Each agent can take on a different role. One agent gathers information, another analyzes the data, a third develops a plan, and another integrates the results into a final recommendation. Just like a human team, they communicate, coordinate, and collaborate to solve complex problems. This is no longer a theoretical idea. Leading AI companies are already developing practical multi-agent technologies. Anthropic is exploring collaborative workflows through Claude and specialized agents. Google is advancing projects such as Project Astra and AI Co-Scientist, where multiple AI systems cooperate on research, planning, and problem solving. Microsoft is expanding autonomous business automation through AutoGen and Copilot Studio. OpenAI is developing projects such as Swarm and Operator, enabling multiple AI agents to coordinate on complex tasks. And Meta is also researching collaborative learning among multiple AI agents. These developments point toward the same direction. AI is evolving from a highly capable individual assistant into a coordinated team of intelligent agents. If generative AI represents the power of the individual, multi-agent systems represent the power of collective intelligence. By combining specialized capabilities, they can tackle problems that are far too large and complex for a single AI system. The next generation of AI is therefore not simply about building a smarter model. It is about designing intelligent systems that can collaborate, coordinate, and achieve goals together. AI is evolving from the genius of one to the wisdom of a team. As we have seen throughout this journey, AI has evolved through several major stages, from symbolic logic, to machine learning, to deep learning, and finally to large language models. For many years, the primary goal of AI research was straightforward: to make AI more accurate, more powerful, and more efficient. Researchers focused on improving prediction accuracy, increasing processing speed, learning from larger datasets, and building more capable models. These technical challenges defined AI for decades. But today, as generative AI and multi-agent systems move into real-world applications, the nature of the challenges is changing. Performance alone is no longer enough. We must now ask much broader questions. Can we trust AI? How can we ensure it operates safely? Who is responsible for its decisions? How can its reasoning be explained and audited? And perhaps most importantly, how should humans and multiple AI agents collaborate within society? These questions extend far beyond algorithms. They involve privacy and data protection, fairness and bias, transparency and explainability, governance and accountability, coordination among multiple AI agents, monitoring autonomous behavior, and the long-term relationship between AI and humanity. In other words, the challenge is no longer simply to build a smarter AI. The challenge is to design AI systems that can operate responsibly within human society. This requires more than advances in computer science. It requires collaboration across engineering, ethics, law, public policy, and social systems. The next generation of AI will therefore be defined not only by technological innovation, but by how well we integrate trust, safety, ethics, governance, and human collaboration into its design. The evolution of AI is no longer just about building more intelligent machines. It is about designing intelligent systems that people, and society as a whole, can trust. Now, let's consider one of the most fundamental challenges of generative AI. Large language models generate responses by predicting what is most likely to come next based on the probability distribution learned from enormous amounts of data. In other words, they are fundamentally smooth prediction engines. Language, images, music, and many other forms of information are represented as probability distributions in a high-dimensional continuous space. The model continuously predicts the most probable next token, creating responses that appear natural and coherent. However, the world in which humans make decisions is not perfectly smooth. In the real world, even a small change in context can completely change the meaning of the same information. Consider a prediction score of 0.49 and 0.50. Numerically, they are almost identical, but in medical diagnosis, financial approval, fraud detection, or safety-critical systems, that tiny difference may determine whether something is considered acceptable or requires immediate action. This is because the real world contains boundaries, points where meaning changes discontinuously, and these boundaries are not fixed numbers. They move depending on the organization, the purpose, the user's role, regulations, and the surrounding context. This explains why generative AI can produce responses that are linguistically correct but still difficult to use. For example, a document summary may read naturally, yet omit exactly the information needed for an important business decision. Likewise, advice about careers, healthcare, or management may be generally reasonable, but without understanding an individual's circumstances and values, it may become incomplete or even misleading. The issue is not that the AI is simply right or wrong. The real challenge is whether the response is appropriate within the correct context. Future AI systems therefore need more than the ability to generate fluent language. They must also recognize contextual boundaries, understand how meaning changes across different situations, and adapt their decisions accordingly. One of the most important challenges in the age of generative AI is no longer predicting the next word. It is understanding where meaning changes, and making decisions that respect those boundaries. That is the next frontier of AI, and the motivation for designing systems that explicitly manage context, boundaries, and decision-making. Let's look at another fundamental challenge of generative AI, the challenge of autonomy. Traditional AI systems were largely passive. They waited for human instructions, processed a request, and returned a result. Today's AI is different. Modern AI agents are beginning to set goals, make plans, execute actions, evaluate outcomes, and improve their behavior autonomously. In other words, AI is evolving from a tool into an autonomous agent. Greater autonomy brings tremendous benefits. AI systems can adapt to changing environments, solve long-running tasks, and collaborate with other agents without requiring constant human supervision. But autonomy also introduces a new challenge. As AI becomes more autonomous, its behavior becomes increasingly difficult to predict and control. The challenge becomes even greater when multiple autonomous agents interact with one another, and with humans and external systems. This interaction can create a phenomenon known as resonance. Each individual agent may behave rationally according to its own objectives. However, when their actions influence one another, small changes can be amplified into unexpected outcomes. Positive feedback loops may cause behavior to escalate. Biases and preferences can reinforce one another. Individual optimization may conflict with overall system goals. And over time, these interactions can accumulate, leading to instability or unintended consequences. The problem is no longer the intelligence of a single AI. It is the dynamics of the entire system created by many interacting agents. As a result, traditional approaches based only on giving instructions and monitoring outputs are no longer sufficient. New risks begin to emerge. Rapid market fluctuations, the spread of misinformation, more sophisticated cyberattacks, conflicts among autonomous agents, and unexpected behaviors that no single developer explicitly programmed. To address these challenges, we need a new design philosophy. We need governance for multi-agent systems, continuous monitoring and observability, mechanisms for human intervention and control, and clear rules that define how humans and AI should cooperate. As AI becomes more autonomous, the central challenge is no longer controlling each individual agent. The real challenge is designing stable, trustworthy systems in which multiple AI agents and humans can collaborate safely and effectively. That is one of the defining challenges of the generative AI and multi-agent era, and one of the central goals of modern AI governance. As we have seen throughout this series, AI has evolved from a tool that assists humans into systems that can make decisions, act autonomously, and even collaborate with other AI agents. This evolution has introduced another fundamental challenge, the problem of trust. In traditional human-centered society, the structure of trust was relatively clear. People relied on credentials, professional expertise, organizational reputation, and legal institutions. When an important decision was made, it was usually clear who made the decision and who was responsible. In other words, we knew whom to trust. The AI era changes this assumption completely. Today, a single decision may involve a human user, an AI model, autonomous AI agents, multiple collaborating agents, external APIs, and real-world systems. As more participants become involved, the decision-making process becomes increasingly complex. It becomes difficult to determine who made which judgment. AI-generated content can be difficult to distinguish from human work. When multiple AI agents collaborate, the path from input to decision becomes even more difficult to follow. Autonomous agents may plan and execute actions on their own, making responsibility less obvious. And because modern AI models often operate as black boxes, their internal reasoning cannot always be directly inspected or verified. As a result, traditional foundations of trust, such as brands, credentials, and institutions, are no longer sufficient on their own. The AI era requires new trust mechanisms. We need transparency, so that decision processes can be understood. We need traceability, so we know who decided what, when, and why. We need verifiability, so outcomes can be checked after the fact. We need continuous evaluation, allowing trust to evolve based on actual behavior over time. And we need governance and accountability, with clearly defined roles, responsibilities, and rules for safe collaboration between humans and AI. Trust in the age of AI can no longer depend solely on the reputation of people or organizations. It must be built into the decision-making process itself. The future of trustworthy AI depends not only on producing better answers, but on making every important decision transparent, traceable, verifiable, and accountable. Designing that foundation of trust will be one of the most important challenges and opportunities of the AI era. As we have seen throughout this series, AI is evolving rapidly. It has progressed from standalone generative AI to autonomous AI agents, and now toward collaborative multi-agent systems. However, while AI capabilities are advancing at an extraordinary pace, the governance mechanisms of human society have not kept up. Today, many organizations can use AI, but far fewer are prepared to govern AI safely and consistently. As a result, many fundamental questions remain unanswered. Who is responsible for an AI's decision? How much authority should an AI agent have? How should responsibilities be divided between humans and AI? Who should intervene when something goes wrong? And can we later verify how a particular decision was made? In many organizations, these basic governance questions still do not have clear answers. The challenge becomes even greater as we move into the era of multi-agent systems. In the future, society will not consist only of people. Multiple AI agents will also participate in decision-making, collaboration, competition, and the execution of real-world tasks. The actors within society itself are changing, yet the governance infrastructure for this new reality is still incomplete. For example, we still lack standardized mechanisms for registering and authenticating AI agents, managing permissions and defining their authority, establishing common rules and operational policies, monitoring and tracing their actions, resolving conflicts between autonomous agents, and continuously assessing risks to ensure safe operation. These are not optional features. They are essential requirements for operating AI safely at scale. The central challenge of AI is therefore no longer the intelligence of the models themselves. The real challenge is designing the rules, institutions, and governance systems for a society in which AI actively participates. We are moving beyond the era of simply developing AI. We are entering an era in which we must design the society that AI will operate within. That is why governance is becoming one of the most important foundations of the AI era, and why new frameworks for accountability, coordination, and decision-making will be essential in the years ahead. Throughout this series, we have explored the history of AI and the new challenges that have emerged through its evolution. AI has progressed from systems based on symbolic logic, to machines that learn from data, to models that understand context through language, and now to an era in which multiple AI agents collaborate to accomplish complex goals. Along with these remarkable advances, new challenges have also become clear. How can AI truly understand meaning? How can we build trust between humans and AI? How can autonomous AI systems operate safely? And how can we establish governance for a society in which humans and AI work together? These challenges cannot be solved simply by making AI models more powerful. What we need is a new design philosophy, one that focuses not only on intelligence, but also on how intelligence should exist within society. Our approach begins with 4 key frontiers. The first is meaning understanding. AI must understand the relationships between knowledge and interpret meaning within context, not just predict the next word. The second is trust architecture. We need systems that provide transparency, explainability, and accountability, enabling humans and AI to build trustworthy relationships. The third is collaboration and co-creation. Rather than replacing people, AI should complement human strengths, allowing humans and AI to create new value together. And finally, social implementation. AI must be deployed in ways that are safe, fair, sustainable, and beneficial for society as a whole. The purpose of technological progress is not technology itself. Technology is a means to create a more human-centered society. Our goal is not to build AI that replaces people, but to design systems in which humans and AI complement one another and work together to build a better future. In the next slide video, we will explore these 4 frontiers in greater depth. We will introduce the ideas, architectures, and practical approaches that can help address the challenges we have discussed throughout this series. We hope you will join us as we continue exploring the future of human-AI collaboration, and how we can build it together.